Time to show how sugars are made. Alright, so this is the story of Emil Fischer and Heinrich Kiliani. These were chemists from back in the day. And you can probably tell that from the pictures, and of course the very popular beers of that century. Okay, so what did these two fellas do? Well, they basically figure out a way of expanding the carbon chain of a sugar to make bigger sugars. So to show you an example, if you consider xylose as the initial sugar in this treatment, what they figure is that if you react this with HCN, typically in the presence of sodium cyanide to kind of make the process go faster, follow that up by reduction, hydride reduction with poison palladium, basically palladium in barium sulfate, and you finish that process up by introducing aqueous acid. What they ultimately find out is that you can extend the carbon chain by one extra carbon, specifically the OH component, the carbohydrate component you see here in blue is what used to be the aldehyde. And not only that, right, but in this process, because you're turning an aldehyde, an sp2 hybridized carbon, into an sp3 hybridized carbon, you get both derivatives of the bigger sugar, right? So these are not enantiomers because it's only that position that's changing. So you have two different sugars. You have, in this case, idose and gulose, which both derive from xylose. So I'm going to show you how this actually happens. It's a pretty clever reaction. Now, granted, if you were to do this for reals yourselves, first of all, I wouldn't recommend you to do it because you need proper training and safety precautions have to be taken because, after all, you're going to be handling HCN, and cyanides, the conjugate acid and conjugate base, which both of them are very, very, very poisonous. But that aside, the mechanism basically starts by protonating your carbonyl oxygen. This is a small equilibrium. You're dealing with a weak acid and the carbonyl, which is not the greatest of bases really. So you'll have a little bit of this, not a whole lot, but this will kind of kickstart the process because you'll protonate that aldehyde, and then the cyanide that's around, either because you just formed it or because you had cyanide, sodium cyanide to begin with, which is a really good nucleophile, will attack that activated carbonyl. So that attack will push the electrons back to oxygen, and now you have this cyanohydrin derivative of your original sugar. Okay, and yes, you are forming both diastereomeric versions of it at this moment, right? You have the OH pointing to the left on the one instance, you have the OH pointing to the right in the second instance. Okay, so that's basically it for the first step, just the treatment with HCN. Then you bring the heavy duty stuff, you bring your palladium, and you proceed to do the reduction of that cyano component, the nitrile component. So here I'm going to spell out, right? So I know in the previous one I just wrote CN for the thing we have there, but that's nitrile, and nitrile, you should remember, is carbon triply bonded to nitrogen. So I'm going to spell that out for the mechanism, and if I ask you to draw the mechanism, then you better spell out these bonds. It's not okay to leave it in condensed form if it is actively involved in the mechanism. All right, so what happens now is that we're going to treat this with palladium and hydrogen. All right, so the way this works out, and I'll show you the catalytic cycle momentarily. But the way that this works out is that in the presence of hydrogen, palladium, neutral palladium, gets oxidized to palladium 2. And it tends to form these square planar complexes, 16 electron square planar complexes. Typically when you do this, you do have a ligand around, typically. If you don't, then the solvents that you use for the reaction, occupies that spot instead of a ligand. But yeah, pretty much this palladium undergoes an exchange, a ligand exchange. So the nitrile replaces the solvent. So one molecule of solvent dissociates from the palladium, your nitrile binds to the palladium. And this happens technically in two steps. There's an insertion followed by an addition followed by an elimination. You don't need to know too much about that, but in case you were curious. All right, so once the nitrile binds to your palladium hydride, right, and you have the two hydrides, right, that used to be H2, one of those hydrides attacks the carbonyl carbon of your nitrile. And those electrons, of course, will move onto the nitrogen to make, an anionic um, imine, technically speaking. And typically this also happens by having the solvent come back in and refill that spot, so you kind of retain that square planar structure throughout. Okay, but then if you look carefully, the hydrides are negatively charged, so 1 minus 1 minus. The nitrile is neutral, the ligand is neutral. So by doing this little change here where the hydride attacks the nitrile, you turn it into negatively charged imine or iminide. And then you only have one hydride left, right? The solvent and the ligand are neutral, so you still have a neutral compound right here. Okay, and then the last thing that happens is something which at first is going to look a little bizarre, but pretty much the nitrogen with its two electrons attacks the hydrides, but it only attacks it as if it were an acid. So it attacks the proton and takes away the proton, and those electrons from the PDH bond simply go back to PD. And another way to put that is that the palladium is now getting reduced back to palladium 0. So you have it basically exit out the cycle. But what you've done now is you've turned that nitrile into an imine. And one thing that I need to emphasize is that for this to work out, you have to make sure that your palladium is screwed over somewhat. You're basically poisoning the palladium by adding barium sulfate. But that poisoning effect makes it so that the palladium is not strong enough to continue reducing this nitrogen. Because if you just use regular palladium, no barium sulfate, you will not stop at the imine stage. This will take you all the way to the amine stage. It will reduce it all the way to NH2 and single bond to carbon. But yeah, so that barium sulfate helps out stop midway through the process. All right, now this is just maybe my own indulgence, but being that my background is in organometallic chemistry, I figure I'll just kind of show you a little snippet of this catalytic process. So yes, you're looking at these square planar complexes, but you start with your palladium 0, probably with ligand bound to it, maybe solvent bound to it, and this starts interacting with hydrogen in the presence of solvent. So you'll have the solvent in there, you'll have your hydrogen, you'll have your palladium. So the palladium interacts with hydrogen, it oxidizes in the process and turns that hydrogen into two hydrides. And you have solvent molecule completing the sphere of the metal. This is known as oxidative addition, mostly because you're adding hydrogen and because the metal is getting oxidized. After that, the molecule is about to undergo a reduction, comes in, and it substitutes one of the ligands. So this is just a regular substitution reaction. After that, you have the attack of the hydride to your nitrile. This is referred to specifically as a hydride insertion. And then once you get to this point, the anionic imine attacks the proton, and the electrons go back to your lead, reducing it. Excuse me, not lead, palladium, reducing it. So this is known as a reductive elimination. It gives you the final product that you're after, and it basically takes the metal back to the initial state where this cycle started from. So this basically shows you beautifully that this process with palladium is catalytic through and through, right? Because you go from oxidizing the metal back to reducing it to the original state, and then this just reacts with another molecule of H2, another molecule of nitrile, and it keeps doing this over and over until you run out of reagents. Okay, so just for your own entertainment, I suppose. All right, so that's the second step of the Fischer-Kiliani synthesis. The third step and final step is the treatment of your imine with water, or to be more specific, acidic water. And all that happens right here is that you're going to turn that imine ultimately into a carbonyl. So first you protonate the imine, so now you have iminium. That iminium is technically an activated carbonyl carbon, so the water that you have in there attacks that carbonyl carbon, kicks electrons back to nitrogen. Now you have protonated water, and here technically the solvent gets involved, but I'm going to do it in one step to save us a little bit of time. uh, Pretty much you have a proton shuffle event where the proton on the oxygen is now going to be given to nitrogen. So now you'll have oxygen becoming neutral and the nitrogen now becomes cationic. And not only that, but that nitrogen is now a good leaving group. So the oxygen, the neutral oxygen with its two lone pairs, it uses one of them to attack that carbon, form a double bond, and in the process kick away your amine, or technically ammonia leaving group in this case, right? So now we end up with the ammonia byproduct and the protonated aldehyde, which then simply the ammonia snatches that proton away from the aldehyde, the electrons go back to the oxygen, and voila, now you have your new aldose sugar that is one carbon chain longer than it used to be. So this is what the Fischer-Kiliani synthesis is all about. And to think that they came up with all this stuff like in the 1800s, it's just outstanding. Just a feat of its own. That's probably the reason why they were very proud of showing those beards, because this is quite the undertaking, and so is the maintenance, and cleanliness of beers. So I guess they both go together. Okay, so in the next video, I'll show you the opposite synthesis. You could even call this a degradation or a decomposition, because we're going to do the opposite that the Kiliani synthesis accomplishes. We're basically going to remove carbohydrate away from the sugar and make smaller sugars. But I'll show you how that happens in the next video. See you then.